In this lesson, we're going to introduce Maclaurin series and how to calculate them for any function. Let's consider a function f of x that we want to approximate by a power series. That is, a series that is in terms of powers of x. And we want to do this around the value of 0. So our function is going to be very, very similar to a polynomial in this way. Now our interest would be in finding what these coefficients are. So to do that, we are going to say, because my series is approximating the function around 0, I want to know what the value of the coefficients would be around 0 as well. So I'm going to substitute x equals to 0 into f of x. That way I get f of 0 would be equal to a sub 0, because every other term depends on x and would be equal to 0 in the evaluation at 0. So this is the first thing that we learned about the polynomial. The first term, or the independent term of the polynomial, is equal to the value of the function at 0. Now let's consider the first derivative. Now, why the first derivative? Because when we consider the first derivative, this term will disappear because the derivative would be 0. And this term would remain by itself. And that is very helpful because we can do exactly the same thing that we just did. So to find the derivative, we do f dash of x. Derivative of a sub 0 would be 0 because it's a constant, plus derivative of a1x would be a1, plus derivative of a2x squared would be 2a2x. Derivative of a3x power 3 would be 3a3x power 2, and so on. Now if we evaluate at 0, we get that f dash of 0 is equal to a1. Now this is a very important result, so let's highlight it like we did the previous one. Now I want to know what a2 is, so I'm going to continue to do this for a few more terms. So let's calculate the second derivative. Second derivative of f is equal to 2a2 plus 2 times 3a3x plus At 0, f double dash of 0 would be equal to 2a2. And I'm going to repeat that 2 more times. So now that we have a few more terms, we can start to see a pattern. So looking at the coefficients, I can see that the pattern is a factorial. So I can write f of 0 is 0 factorial times a0. F dash of 0 is 1 factorial times a1. F double dash of 0 is 2 factorial a2. The third derivative at 0 is 3 factorial a3. And the fourth derivative at 0 is 4 factorial a4. So this leads to the general pattern that actually an should be the nth derivative evaluated at 0 divided by n factorial. So with this in mind, I can define my polynomial f of x as a polynomial that goes from k equals to 0 all the way to infinity, because it's an infinite series, of the coefficient f nth derivative of f at 0 n factorial times the power of x to build the power series. So what this results in is what we call a Maclaurin series, which is a power series approximation to any function f of x in the vicinity of 0. So how do we know this works? you can take any function and graph it against the Maclaurin series, and you will see how close the two functions are. Here you can see in red the function 1 over 1 minus x, and in green the approximation with the Maclaurin series. Each of the iterations that you can see here represent the addition of one more term of the series. And we are seeing that as I increase the number of terms in the series, the more similar is the polynomial to the original function. However, you can also see here one limitation, and it is that even though my approximation is getting very close to the function in the vicinity of 0, when I look at x values that are closer to 1, I can start looking at the difference between the polynomial and the original function. So this tells you that this Maclaurin series is a good approximation of the function around 0, in a vicinity of 0, but not necessarily throughout the whole domain of the function. So you need to be careful about that. This area between -1 and 1 in particular is the convergence region for the Maclaurin series for this function. As you can see, the closer you get to -1, the different that the two functions will start to look. However, this polynomial is going to be convergent between -1 and 1, and not convergent for 1 and -1. So we can determine, and we're going to do that a little bit later, what the radius of convergence is for this Maclaurin series. So I want to show you now how this Maclaurin series is obtained for the function 1 over 1 minus x. So let's consider the function f of x equals 1 over 1 minus x. And in order to find the coefficients, we know we need to find the derivatives of this function and evaluate them at 0, except for the first term that we can find by substituting 0 into the expression. So that is going to be 1 over 1 minus 0, and we know that that is 1. For a1 is going to be the first derivative evaluated at 0 divided by 1 factorial. And the derivative of x is -1 over 1 minus x, everything squared, times, because of chain rule, the derivative of 1 minus x, which is -1. So my first derivative is 1 over 1 minus x squared. When I evaluate it at 0, I get 1 over 1 minus 0, everything squared, and that is also equal to 1, which means that a1 is also equal to 1. Now I'm going to repeat this process for a few more terms, and then we will put them together to build the polynomial. So now that we have the coefficients, we can build the polynomial. So all of the coefficients turn out to be 1. So the polynomial is simply 1 plus x squared plus x power 3 plus x power 4 plus etc. Only powers of x.